Okay, I wanted to go over a few things related to equilibrium. So one, write equilibrium expressions, looking at solids and how they dissolve. So we'll call the solubility product and equilibrium. And then finally touching on acids and acid dissociation. So the idea is that we're using equilibrium to describe a variety of different things, but the way we do it is always going to be the same. So first, let's get a handle on the equilibrium constant, how we can describe that. So here's a reaction. I'm taking sulfur dioxide, combining it with oxygen, and I'm making sulfur trioxide. Notice these are all gases. And this exists in equilibrium, so indicated by the double arrow. So this means that if I look, I'll find some of these, and some of these all floating around. And when it gets to equilibrium, the amount of products being produced is equal to the amount of reactants being produced, right? So there's a balance. It doesn't mean that I have equal numbers of these products and reactants. It just means that I'm creating as many products as I'm destroying in the reverse process. So it's a balance between the rates. Okay, so we want to describe this. So we get equilibrium, we want a mathematical way to describe this, so we come up with the equilibrium constant. So our K is going to be the concentration of our products raised to their coefficients divided by the concentration of reactants, right? So roughly it's products divided by reactants. And specifically, it's going to be the molar concentration of SO3 raised to the power of its coefficient, right? Divide this by SO2 raised to its power of its coefficient times concentration of O2, and its coefficient is 1, so I'm just raising it to the power of 1. Right? So really important and a common mistake, sorry, I'm not multiplying this by 2, I'm raising it to the power of 2, so I'm squaring this. If I wanted to solve for the concentration of SO3 and I knew everything else, I would plug in the numbers and I'd have to square root everything else to get there. So this is a common mistake, right? So I have 2, and here, remember, I presume this is a 1. We just leave it off because we like doing that in chemistry. And so I'm going to raise that to the power of 1. So let's look at another example. Let's take this one, PCl5. So I'm going to look at PCl5. And I'm going to combine that with water, and this is going to produce hydrochloric acid and POCl3, so something else. So states are really important here. So notice I'm going to write an equilibrium constant, right? So my equilibrium constant, K, is going to be something about the concentration of the products raised to their coefficient divided by the concentration of the reactants raised to their coefficients. But notice that when I'm writing equilibrium, I'm going to leave off solids and liquids. So I'm only going to include gases when I'm writing equilibrium or aqueous solutions. So, and the point being that really the concentration of my solids not really changing, right? I have this hunk of solid and I add to it or subtract from it, but the concentration of that, right, the number of moles per liter of that solid is not changing. The same is true for liquids. So we do things in water, which is, we're like 55 molar, and I'm going to add a water molecule or two. Really, I'm not changing the concentration of that. So let's draw it out first, and I'll show you what this looks like. So I'm going to take my concentration of my products, right? So I'm going to have concentration, my molar concentration of HCl raised to its coefficient times the molar concentration of POCl3 raised to its coefficient, which is 1, divided by just H2O molar concentration. All right, so notice I'm just leave off the PCl5 because it's a solid. So it makes the math a little bit easier, but conceptually it's really important, right? So I have this stuff that's in equilibrium. Some of that solid's being used. I have to have some of it, but the amount really doesn't matter. I just have to have enough of it for this to go. So I'm going to have some of the solid. It's going to combine with the water. I'm going to get this stuff, and it's in equilibrium, so some of my products are also regenerating some of my reactants. So it's another reaction. So every reaction that we write is going to have a different equilibrium constant. And we can write equilibrium constants for all sorts of reactions that you've already seen before. So let's think about this one, right? So here I'm taking magnesium chloride as a solid, and I'm dissolving it, and I'm getting the 2 ions out, right? So this is a dissociation. This is an ion dissociation reaction. And it's nothing new, right? We've seen this before, but I can write this in terms of equilibrium. So I can say, well, this is going to have some equilibrium constant, and this is going to be, again, the products, concentration of the products over the concentration of the reactants and I'm going to leave solids and liquids off. So let's see what I get. Well, I'm going to have my concentration of my magnesium ion raised to its coefficient, which is 1, times the concentration of my chlorine ion. So notice I get 2 of these, everyone, so I'm going to erase this. I'm going to divide that by my solid, which is not there, so this is it. Right? So this is a way of describing the equilibrium of solubility of something. So if something dissolves well in water, I'm going to get a lot of products, so I'll have a large K value. If something really doesn't dissolve well in water, well, I'm going to have a very small K value. I'm going to have mostly reactants at equilibrium. Right? So this is a way of describing solubility. And as we do with Ks, right? So this is called a solubility product. So it's a K. It's the same way we calculate all of our equilibrium constants. I'm going to give it SP for solubility product, and it's equal to the ions. So it's another way of thinking about reactions that we've seen before. So let me take a minute and show you what this looks like. So FET has a nice simulation which describes some of this, right? So here I'm taking something, what is this, strontium phosphate. So I'm going to put a little strontium phosphate into water. Some of it dissolves, and I have ions floating around, but notice that some of it didn't dissolve and just sinks to the bottom, right? And if you watch really carefully, you'll be able to see that once in a while, some of that stuff that is dissolved in solution sticks to the solid and becomes the solid stuck at the bottom. And once in a while, some of that solid stuck at the bottom sort of dissolves and goes off into solution. So we have forward and reverse reactions that are happening in this. I have things dissolving and then coming out of solution, crystallizing. So and this is having both a forward and reverse reaction. But notice what happens if I add more. Right? So we leave solids out of our equilibrium calculation because the amount of it doesn't really matter, right? So if I add more, what happens to the amount of stuff floating around? Well, nothing. So I get the same amount of stuff floating around regardless of how much solid that I have. So for this reason that we leave all of the solids and liquids out of our equilibrium calculations and out of our equilibrium equations. So this is one way of writing dissociation. So the last thing we want to do is just use acids, right? Acids are doing a similar sort of thing. So I have an acid dissociation reaction, and I can write that with equilibrium. Right? So here's my acid reaction. It's more interesting to do this for weak acids. So this is my weak acid, acetic acid or vinegar, that is going to combine with water, and I'm going to get out this thing and a hydronium ion, right? So let me be careful about this. So in my acid dissociation reactions, I'm only ever moving a single hydrogen, and I'm going to move the hydrogen to that other thing, right? So this is my acid, this is my base, water's acting as my base. I'm going to move one hydrogen across, and I'm going to end up with my conjugate, right? Conjugate base and my conjugate acid, right? So that's what I think about it. So this is donating the hydrogen in the forward direction. This is donating the hydrogen in the reverse direction, right? So there's a connection. So my acid and my conjugate base always differ by one hydrogen, and my other acid-base pair differs always by one hydrogen. So we're going to write this in terms of equilibrium, right? So I can say, well, what is the equilibrium expression for this? Right? It's going to be different for every reaction, so let's figure this out. So this is already balanced. I'm not going to worry about that. And again, my K is going to be the concentration of my products raised to their coefficient divided by the concentration of my reactants raised to their coefficients. And I'm going to leave liquids and solids off. What do we get? So my products, right? So my product side, I have my acetate polyatomic ion raised to its coefficient of 1, and my hydronium ion raised to its coefficient of 1. And I'll divide that by just the acid itself, so the conjugated acid. And I leave water off. So this is another equilibrium constant. Because we like doing this in chemistry, we're going to say, well, this is a Ka for an acid dissociation. So it's a specific type of reaction, but it's the same way that we've been determining K. And it's going to exist of these two things. I'm going to have my conjugate base times the hydronium ion divided by my acid when the hydrogen is stuck onto it. And that's the way that we write acid dissociation reactions. Again, K is nothing special about it, that we use it the same way in different circumstances, but we use it to describe different types of chemical reactions. Anyway, hopefully this makes sense to you, and if you have questions, don't hesitate to ask me. Take care.